Okay, so first midterms, I finished grading them. I will upload the solutions on Auto class today. I will not upload the grades in Auto class, and I will not send you your graded midterms by email unless you ask for it. There is, in Auto class, I created a choice where you can ask for your graded midterm papers to be sent or not. So if you fill that and if you ask for your midterms, your grades, I will just send them by email. I will send them all anyway after the second midterm. Well, the problem is you will probably not be able to find me. If you have any questions, of course, about the solutions or about your paper, etc., you can give it a try. Yes, any questions? Well, you see, what we had done in that problem, you see, what we were discussing first, how does the electric field transform from one reference frame to the other reference frame? And to study that, what we did was we first made the argument that it's not important how the electric field is created. Its transformation properties depends only on the point and the electric field and magnetic field at that point. It doesn't depend on how we create that electric field at that point or that magnetic field at that point. So we said that, okay, if you want to find the transformation properties of the electric field at a given point, then one way of creating that exactly the same electric field at that point will be to consider just the parallel plate capacitor. Just two parallel plates, you can adjust the surface current density such that it creates exactly that current at that point. Of course, the electric field at different points will be different in general, but we don't really care about that because as we already said, the transformation properties of the electric field depends only on the electric field at that point and only on that point, not the electric fields at other points. And then we said that, okay, so let's just look at this system, capacitors, which creates an electric field in this direction. Let's say they have a surface current density given by plus sigma 0 and minus sigma 0. In the other reference frame, which is moving relative to this one, so let's say in a different reference frame in which these are moving with speed v, the current densities will be different. Mainly the difference will be due to this Lorentz contraction, since the charges will be the positions of the length over which the charges are distributed will be contracted in one dimension. The charge density sigma will be larger than sigma 0. And sigma will be just gamma sigma 0. And now we said that, okay, in this reference frame, the electric field is given by let's call it E0, sigma 0 over epsilon 0 in the minus z direction, let's say. In this reference frame, the d, well, nothing except on sigma, nothing actually changes. So the electric field in this reference frame will be sigma over epsilon 0, again in the minus z direction, which is nothing but gamma times E0. Well, in this case, the electric field is parallel to the direction of the velocity. So this was what we had derived. And then we said, okay, what if the electric field is perpendicular to the direction of the velocity? To make that explicit, we use this notation to show that the electric field is perpendicular to the velocity. not to the surfaces. And then we said, okay, let's consider the case when if you have an electric field and then you have another vector, which is the velocity vector, you can always write the electric field as the parallel component plus the perpendicular component. We see that it is the perpendicular component that is transformed, that changes as you change your reference frame. The parallel component, let's say this is plus sigma, this is minus sigma 0. In the alternative reference frame, this distance will be d0, this distance will be d, the charge densities will be sigma, and hence this will be the electric field. This time let's denote it by parallel. Parallel meaning that it is parallel to the velocity. Now we see the only difference between these two reference frames is the d. d is Lorentz contracted, so d is d0 over gamma. But sigma doesn't change because sigma, the charges are distributed in an area which is perpendicular to the velocity. No directions in this area is contracted, so sigma doesn't change. But the electric field depends only on sigma of this parallel plate capacitor, not on d. So the electric field does not change. So we know how the components of the electric field change as we go from one reference frame to the other reference frame. Now you see, when we were writing this for the coordinate, when we are writing x prime is equal to gamma x minus ct, vt, t prime is equal to gamma t minus v over c squared x, etc. We are assuming that at t equal to 0 and at x is equal to 0, the origins are overlapping. So we have two origins that overlap. Then we looked at the example of a point charge. Now what we were considering first was that at t equal to 0, my charge is at the origin. That was what we had considered. Let's say we were looking at this in a time, let's say t, at which my particle is in the origin. And the origins of my reference frames are overlapping. And then we derive the expression that at this point, the electric field was gamma over delta cubed in the radial direction, delta squared, q over 4 pi epsilon 0. Now, this is the electric field at this point, and this is the radial r hat vector. Now, I don't have to choose my coordinate axis such that my charge is at the origin. So I can say that I have an arbitrary origin. It's exactly the same reference frame. It's just the origin is shifted. And then the particle, I can just shift my time in this reference frame. I mean, since they are not moving relative to each other, they agree on the time measurement, they agree on the position measurement, etc., length measurements, etc. They are not moving relative to each other. I'm just shifting my origin. In this new reference frame, the particle is at the point r of t at the time t. T is measured in this reference frame. So if you want to find the electric field at the point P, this would be q over 4 pi epsilon 0, gamma over delta cubed, r minus r of t. Well, you see, the electric field at this point will still depend on this distance, the coordinate of P relative to this point, and this r hat vector over there will be just the unit vector pointing from here to there. Well, let me also correct that one. That is delta cubed times r. Delta is not the magnitude of r vector. Well, you see, in the first case, we are choosing our coordinate axis in this different reference frame such that the charge is at the origin. But then I said that, okay, you don't have to have the charge at the origin. You can have your origin at some arbitrary point. The position of your particle will be r of t at a given time, t. And your friend was saying, which time is this? So, but you see, once I get that expression over there, well, there's no question about the time in that case. But you see, at the next time, my particle will not be over here. It will have some different origin. So I can say that I can just compare the electric field in this coordinate axis and in this coordinate axis. Now, these two reference frames, so I'm trying to avoid the use calling them different reference frames, but they are different reference frames. The reason why I'm avoiding them is that these two reference frames are not moving relative to each other. So if I have two different reference frames that are not moving relative to each other, you see that r vector is nothing but the vector pointing from my charge to the observation point. I do the same thing over here. So that r vector, I have to replace it with the relative position vector of the observation point relative to my charge, which is nothing but the position vector minus the position vector of my charge. And hence delta should also be modified accordingly. But from this perspective, there is no ambiguity here. Everything I'm measuring in a single reference, in two different reference frames, but these two reference frames, they agree on the time, they agree on the length, since they are not moving relative to each other. Well, you see, that is kind of the funny part. We didn't go into the technical derivations of that. It's kind of boring. But we did drive this. That is, the detailed derivation is in your book. We did drive it using the retarded potentials. And even in that case, it turns out that the electric field of a charge moving at constant velocity is radial. Radially out from the actual position of the charge. You see, the question is the kind of, let's say, the funny part is the electric field at this point is determined by the charge, not at this point, at the same time. It is determined by the position and the velocity of my charge over here. This is the point at which my particle is at the retarded time. Nevertheless, the electric field at the point P, although it is determined by the position and velocity of my particle at the retarded position, is still radially out from the current position of my charge. You see, you can think of it like this. If you have this moving particle, the zeroth order approximation would be, I'll just use the Coulomb gauge. Not the Coulomb gauge, but the Coulomb law. 1 over 4 pi epsilon 0 q over r squared in the radial direction. But then there is the other correction to that. The correction will tell you that, okay, there is a changing electric field, that there will be a changing magnetic field, so you can calculate the magnetic field. But there's a magnetic field which will create a changing electric field. You can add that correction to the electric field. But this correction to the electric field creates a correction in the magnetic field. But then this second correction to the magnetic field creates a correction in the electric field. The third correction, and so on. So you obtain an infinite series. When you summed up infinite series, it turns out that the electric field at this point is actually in the radial direction, still from the actual position, not the retarded position. But the retardation effects, they are already taken into account. In which reference? These reference frames. Sure, in these reference frames, the particle is moving at a constant velocity v. Other questions?
Hocam şimdi biz hep hani tek direction'da hareket ettiğini düşündük. Mesela hani sen de y direction'da hareket etsin. O zaman dedim.
Yeah, you see, first of all, are we talking about constant velocity or changing velocity? Constant velocity. What is your x direction? I choose it to be the direction of my velocity. As long as the velocity is constant, it's actually moving in a single direction. Of course, you can choose. I mean, in these problems, I have chosen my coordinate to be. You see, when I have this convergent properties, I'm not talking about x, y, or z direction anymore. That was on purpose. It's the direction parallel to the velocity and the direction perpendicular to the velocity. And since the Lorentz transformation relate two reference frames that are moving at constant velocity to each other, well, there is a unique parallel direction to the velocity and a unique perpendicular direction to the velocity. So it's not about x, y, or z coordinates. The particle can be moving in any direction that you like. But most of the time, the direction of the velocity of the particle, since the coordinates, we are free to choose it in whichever way you like. Most of the time, we either choose it in the x direction or in the z direction. But that doesn't mean that it is moving, that does mean that it's moving in a single direction, but that is the motion with constant velocity. It's only in one direction. Of course, you can just choose your x, y, or z axis arbitrarily, not necessarily in the direction of the velocity. You are also free to do that. It's just your expressions will be more complicated. You know how the rotations change your coordinates. So you do two things. One, you consider a boost in the direction of the velocity and then rotate your coordinate axis. But at the end of the day, you don't really gain anything except in some more complicated expressions. Not a bad homework question. Okay, now let's continue with what we were trying to achieve on last Friday, or Monday. If you remember what we were looking for, okay, so here we had derived the transformation properties between two reference frames, that the component of the electric field parallel to the velocity doesn't change, whereas the component perpendicular to the velocity gets multiplied by this factor gamma as you go from one reference frame to the other one that is moving with the velocity v. But there is an assumption here, and that assumption is these laws are valid in the absence of magnetic field. So we don't know if magnetic field will play any role in these transformations or not, if there was some magnetic field. And now that is what we are trying to do, what we were trying to do on Monday. And the thing that we will be trying to do is, now we will be considering a third reference frame. Now the first reference frame. Which we call S0. I have these two parallel plates, charges plus sigma 0, minus sigma 0. I have an electric field E0 and the magnetic field B0, which is 0. Then I call the second reference frame. Which I call S prime. Now in this reference frame S prime, the charges are moving with velocity v, or let me call it u this time. Relative to S, S0. In this reference frame, I have an electric field in that direction, but I also have a magnetic field. Because I have moving charges. And the electric field is just sigma over epsilon 0. Let me choose my coordinate axis also, x, y, and z. Sigma over epsilon 0 in the minus z direction. And the magnetic field is mu 0, sigma u in the x direction. Or if you like, the electric field is equal to gamma times E0, whereas the magnetic field, mu 0, epsilon 0, times V cross B, E. Now U cross, E cross U. And if you like, you can also write this as minus 1 over C squared minus U cross E. Well, you see, U is the speed of the plates in my S prime reference frame. But minus U is the speed of my S prime reference frame relative to the S reference frame. You see, if I'm moving in this direction, then the plates will be moving in that direction. So the direction of the, relative to me, the direction of the plates relative to S prime reference frame is opposite the direction of me relative to the reference frame in which the plates are at rest, S0 reference frame. So now here, the second reference frame is a reference frame in which we have both an electric field and a magnetic field. And now we will look at the third reference frame, well, let me call this velocity v. V is relative to S prime, and V prime, or let me call it V0, relative to S0. So once I have a third reference frame, I can talk about its velocity relative to one of the reference frames or the other one. And I will call the velocity of this third reference frame relative to S prime as V and relative to S0 as V0. Now my purpose, well, if you like, we can write down the electric field in that reference frame also. Well, let me just put primes over here. These primed electric and magnetic fields are in the reference frame S prime. And in the reference frame S, And let's say this is gamma, but gamma u. It is 1 over 1 minus u squared over c squared under the square root. Since we have many velocities now, we will have many gamma factors. So it's wise to specify which gamma is referring to which speed. Now in this new reference frame, okay, let me just make a slight one more chain, that sigma is sigma prime. The electric field is, now in this reference frame we have sigma. Okay, now let's pay more attention. Now u, I said that u is relative to S0. That's not correct. U is relative to S prime. U is the, okay, what should we call u? Should u be the speed of the plates or the speed of the reference frames?
Speed of the reference.
Okay, so u is the speed relative to S0. In that case, the plates are moving with a speed minus u. Are you following? So the speeds are kind of getting confusing. So we have the relative speeds of reference frame, we have the speeds of the plates, etc. So we have to be precise about which speed is which. So your friend suggests that we should use u to denote the relative, the speed of the reference frame S prime relative to S0. Then the plates are moving with a speed minus u. Well, let me just, now the u might be pointing in that direction. So minus u is pointing in this direction, so b is still in that direction. So here I have a minus sign, here I have a plus sign. Okay. Well, I wanted to avoid changing many things, so u is in that direction. So I have one reference frame in which the plates are at rest. And then I go to a reference frame which is moving with a velocity u, but that velocity is towards your left. So in this reference frame, in this S prime reference frame, the plates are moving in that direction, minus u, with a velocity minus u. So let's see if I did everything correct. Then E cross B B prime still has this expression. It is in the x direction, which is pointing out of the screen, is just E cross minus u. So that's why I have this minus sign over there. So if I just change their places, it just becomes u cross E. So this is and that is E prime. So basically what this tells you is that, well, let me also put the gamma. Now let me await the gamma. Okay, so what this tells me is that you have one reference frame where there is the electric field. The electric field, and then you go to another reference frame which moves in a direction perpendicular to the direction of the electric field. And you don't have any, in your initial reference frame, you only have an electric field, you don't have any magnetic field. Then you go to a different reference frame which is moving at a speed u, which is perpendicular to the direction of the electric field. In this new reference frame, there is a new electric field which is obtained by the electric field in your first reference frame by multiplying it with this gamma factor corresponding to this transformation from one the first or the second reference frame. And in this new reference frame, although initially there was, in your initial reference frame, there was no magnetic field, now there is a magnetic field in this new reference frame, and the magnetic field in this new reference frame is just the velocity of, the relative velocity of your reference frame's cross product with the electric field in your new reference frame. Now we go to the third reference frame, which is moving with a velocity v. Nope. Let me call it this reference frame S. Velocity of S relative to S prime, I call it V. And its velocity of S relative to S0, I call it V0. Well, since it's moving with a velocity V0 relative to S0, I already know how the transformation from S0 to that new reference frame is. E prime will be equal to gamma V0 E0, and B prime it will still be 1 over C squared V cross E. There are no primes in this one. Now this is, of course, the electric field is written in terms of the electric field in the S0 reference frame. Now what I would like to find is the transformation property of the electric and magnetic field as I go from one reference frame, which has both an electric and magnetic field, to a new reference frame. So I'm not really interested in going from S0 to S that I already know. What I'm interested in is how do I go from S prime to S without knowing the existence of S0. That's what I would like to do now. Correct.
İkinci referans frame'e geldiğimizde bir manyetik alan var. Çünkü hareket ediyorlar. Fakat bu ikisi birbirlerine göre aynı hızla hareket ediyor. Yani yük ya da var neyse. Fakat birbirlerine göre manyetik alan oluşturmuyorlar. Yani ilk mesela ne diyeyim, ikimiz aynı hızla hareket etse birbirimize göre manyetik alan oluşturur mu?
Well, you see, the picture you have, the description of the phenomena changes as you go from one reference frame to the other reference frame. You see, if you look at, we were discussing this example of 2-point charges. Well, it's basically the same example. If you have 2-point charges at rest in one reference frame, well, there's an electrostatic attraction. I am the observer, I'm not the charges. I'm looking at those charges, and what I see is that there's an electrostatic force between them. That will be my description of the phenomenon. Now, I go to a different reference frame, which is moving relative to these charges. So in this new reference frame, the charges are moving. So they will exert, and I'm, again, the third observer, I'm seeing them as they are moving with the same velocity in the same direction. What I will see is that they are exerting an electric force to each other and also a magnetic force to each other. Now, what do you mean by magnetic field relative to each other? Do you mean the magnetic field in the frame in which one of them is at rest? So what do you mean by magnetic field relative to each other? Sure. But you see, no, you see, you don't talk about magnetic fields relative to things. The only thing, well, that's not precisely correct. You talk about magnetic fields in a given reference frame. So which reference frame would you like to talk about? Which reference frame do you pick to study your problem?
İkisini birden şu an şey yapamıyorum, yani birleştiremiyorum.
You see, the description will be different. I mean, just like this. Are you at rest? No, you are not at rest. You are at rest in your reference frame, not at rest in my reference frame. So you and me, we have different description of the same phenomena. You are still there. The phenomena doesn't change, but we have different descriptions of it. The same thing happens over here. If you are considering, if you are in this reference frame, you will describe this phenomena as if there are, the two plates are exerting electric forces on each other. That will be your description. I go to this reference frame. In this reference frame, I will describe it as, okay, there is a relative electric force and also the magnetic force between these two. We are describing the same phenomena, but our perspectives are slightly different.
Ama fazladan bir force eklenmiş olmayacak mı reference frame'inde?
Well, how does the force transform? Is the force a frame-independent quantity? The force depends on the reference frame. Yes. But then the problem is this one. So on one hand, we know how the forces in general are transformed from one reference frame to the other frame. Okay? On the other hand, we know how much forces that the charges feel. We have the Lorentz force law. We can calculate the force directly using only the electric field here. Or we can calculate the force, again, directly using the electric and magnetic fields here. So do these two forces satisfy the transformation property of a force? And what turns out to be, yes, they are consistent. If you want, you can calculate the force here and transform it to this reference frame. Or you can calculate the force directly here. They give exactly the same result.
Hocam şimdi şurada işte plaklar var, işte duruyorlar. Biz de duruyoruz. Manyetik alan yok. Ama ben hareket etmeye başlayınca manyetik alan oluştuğunu görüyorum.
You are observing a magnetic field, yes.
Peki benim elimde pusula varsa, ilk başta durdum, pusula işte kuzey kutbu tarafı gösteriyor. Ama ben hareket etmeye başlayınca manyetik alandan dolayı değişecek.
Okay.
Ben o zaman nasıl anlayacağım? Yani?
But you see, you are not talking about the same compass.
Ama ben tutuyorum değişiyor.
Well, but you are changing your reference frame. So there are two different compasses. So it's not a great surprise that they will be pointing at different directions. Now, the interesting question will be, let's look at this case. You have a compass staying over here. And the parallel plates are at rest in the reference frame in which the compass is at rest. Then we go to a different reference frame. You see, in this reference frame, the compass doesn't feel any magnetic force because there is no magnetic field created. So the compass is not affected by the plates or the wires, whatever you want, whichever system you have. And then we go to a different reference frame in which now there is a magnetic field, in which the compass now should feel this magnetic field and should deviate. So how are these consistent? But then I should ask this question. What do we call a compass? We call a compass a magnetic dipole with no electric dipole. Okay? My next question, how does a magnetic dipole transform from one reference frame to the other one? So will it still be will it still have zero electric dipole moment in the new reference frame?
zaman yine durgun olacak yani. Pusulada hiç oynamayacak.
Well, if our framework is consistent, it should be stationary. Now, of course, there is the other problem. What do you mean by stationary? You say we are talking about some direction, right? But in one of your homeworks, for example, you were looking at the angle that the mass makes in different reference frames. Well, directions is not a frame-independent quantity. Directions also change. You see, if I have a compass that is pointing in that direction, if I go to a different reference frame, you see, just take this compass, construct a right triangle over here, you can determine the direction, this angle, but in this new reference frame, this length over here will be contracted, whereas this length will not be contracted, and hence the angle of the compass will be different in a different reference frame. But that's mainly because the north will also be in a different direction. So all of these you should sum up all these effects. By all these effects, I mean, in a different reference frame, the north pole will be in a different direction. The magnetic dipole moment, maybe it will have a different value, because both a vector and a magnitude, both of them can be different in a different reference frame. The electric dipole moment can also be different in a different reference frame. So you should all take into account the change in the direction of the north pole, the change in the magnetic dipole moment, the change in the electric dipole moment. They should all be consistent. If your compass points towards the north in one reference frame, it should still be pointing toward the north in the different reference frame, but of course the north will be in a different direction. The reason why it is pointing in that direction might be different, but it should still point in the direction of north in that new reference frame. It's not just one or two properties that are changing, all the properties might be changing. The observations should be consistent. The physically measurable things should be consistent. If something is at rest is not accelerating in one reference frame and it is accelerating in the other reference frame, then you have a problem. At least that shouldn't happen in special relativity. It can happen in general relativity, but not in this framework. Other questions? Okay, so let's give a 10-minute break and then we will continue.